We're trying to find the range of the expression sine theta plus cosine theta. Now we already know from just basic trigonometry that sine and cosine are both trapped. I'll just write down sine here. But sine theta is bounded below by -1. That would be at what, 3 pi over 2 or 270 degrees. And at pi over 2, sine is equal to 1. Okay, so that's the bottom and the top of the unit circle. So this is often written in this fashion. The range, not the domain. The domain would be all real numbers, right? But the range of the sine function is -1 to 1 inclusive. That's why we do the square brackets, okay? And something similar for cosine, okay? Now what we want to find now, though, is the range of sine of theta plus cosine theta. You can't just add the ranges up and get 2. It's not quite that simple. There's a way to do it without calculus. I'm going to do it via the Cauchy-Schwarz Inequality. It's really very, very straightforward. No derivatives, nothing, just a well-known inequality. Handles this task quite easily. Now, y'all, in this particular case, it's clear that n would be equal to 2. This is just one version of the Cauchy-Schwarz Inequality. You could write it just as the dot product. The summation here is sometimes called a dot product. Take the square roots, but I think it's a little more instructive to do it this way. So let's take a look here. Sine theta plus cosine theta, which is what we're interested in finding the range of, quantity squared. Now, writing it like this is useful. And again, I'm really, I'm a stickler for putting the ones in there. Some people leave them out. But when I was trying to learn it, that frustrated me quite a bit. People would just say, oh, there's an understood one there. Well, here it's explicitly your A1, B1 is sine theta times 1, and then your A2, B theta. Excuse me, your A2, B2, A sub 2, let me erase that. Okay, A sub 2 times B sub 2. So you see it's exactly a direct handoff to this. You can see that this very first line here is exactly in this form, okay? Now, so what we can do at this stage is just take advantage of the fact that that sine squared theta plus cosine squared theta is equal to 1, right? And so we get this piece right here is just equal to 1. That's the basic unit circle identity just in terms of the angle. Sine squared plus cosine squared theta, let me just write it directly underneath, is equal to 1. Okay, and again, y'all note that this right-hand side is exactly, these are your a sub I squareds right here, your a sub I squareds and your b sub I squared. So this piece right here is the left-hand side of the inequality, and this piece down on the next line is the right-hand side of the inequality. And again, since sine squared plus cosine squared is equal to 1, we get that this expression is less than or equal to 2. Now we're interested, though, not in the squared version of things, okay? We're interested in what is the range of this, right? Okay, so we take the square roots of both sides, and notice something that's important here that sometimes some people don't know this really, but if you have, let's call it cap A if you want to, the square root of cap A squared, providing A is non-negative, is equal to the absolute value of A. That's you can think of that other than that cumbersome piecewise definition. This is the definition of absolute value. Just think about the Euclidean norm. For complex numbers, it would be a squared plus b squared, right? So for this, the square root of a squared is the absolute value of a, and so that's exactly what I did. I took the square root of this, which makes it the absolute value of the object, okay? And then when I took the square root of 2, of course, I get that, okay? Now notice the basic properties of absolute value will indicate this absolute value statement. You can strip away the absolute value bars, okay, and get what we were looking for, okay? And I'll drop the parentheses. I like using the parentheses for the sine functions because they are functions and the parentheses get dropped frequently, so I just like to remind myself. But so we have this going on. And we've completed the problem. We have shown that the range of sine theta plus cosine theta is between minus the square root of 2 and plus the square root of 2. And if you want to write it like a textbook would expect you to write it, the range of this expression is in this closed interval. Okay. Now, y'all, we're done with the question. That's the answer. This is the answer to the question. The range of that guy is this interval of numbers. And you could actually graph this. It's very hard to graph it by hand, but plug it into your calculator and graph it, and you'll see it maxes out at the square root of 2 and mins out at minus square root of 2. Now, this, I'll just go beyond what the question asked. You can determine when it achieves these maximum values just by equating. Let me write this, the equality condition for Cauchy-Schwarz. If you write down sine theta, and again, just for emphasis, I'll write down sine theta over 1. If the ratio of the coordinates is the same thing, it's constant, okay? Think of these as vectors if you want, but the equality condition for this, which will correspond to the max and mins, happens exactly here. Okay. Again, if you want to think of this as a sub 1 over b sub 1, a sub 2 over b sub 2, all the way through, when these things are scalar multiples of each other, that's when equality happens. But equality would mean it's equal to minus root 2 or plus root 2, right? But notice this happens exactly at theta is equal to pi over 4, just in the interval from 0 to pi over 2. But it also would happen, for, let's see, I guess, odd and even multiples, it would happen also at 3 pi over 4. That would probably be negative right there, okay? And then it would just be periodic and so on. So you would have these odd multiples of pi over 4. You hear that in your trig class all the time, where this expression will oscillate between minus root 2 and root 2. But anyway, this is the answer to the question. I hope you enjoyed that, and I really like the Cauchy-Schwarz inequality. It's very nice. You didn't have to take any derivatives, find horizontal tangent lines, anything like that. No calculus involved, just a very simple application of Cauchy-Schwarz inequality. And let me go ahead and write down the range here, minus root 2 to root 2. Thanks for viewing.